Hey guys, this is going to be a new type of video that I'm trying out. It might be a little longer, it might be a little wordier, but I hope that the information in this video is going to be very helpful to people in the community. So, um, this video is going to focus more on the theory or science or reasoning behind why certain things in Airsoft work, not necessarily about certain parts or brands or anything like that. Hopefully I can turn this into a series. We will see about that. But today we're going to focus all about Hopups. Most of this information is going to be focused towards beginners. It does not mean that if you are intermediate or advanced in the airsoft hobby and you kind of know your stuff that you're not going to find any information in this video at all. But what it means is that I'm probably going to hope that if this turns into a series, that this series can help raise the knowledge floor in the airsoft hobby so that there's a lot less misinformation and kind of opinions not based on fact or trial and error or reasoning about going around about why stuff works and why stuff doesn't work. So here we go. So hop-ups, why do they work? That's going to be the topic of this video. And I want to start off by drawing comparisons to other sports, right? So you have baseball, tennis, soccer, golf. A lot of popular sports that I'm sure you guys should know at least one of these, right? So in all these sports, the thing they have in common is they involve balls or spheres that are thrown, hit, or kicked, and they can spin. And when I spin, so let's say like a baseball curveball, right? After it's thrown by the pitcher, it will go up and then it will curve down and to the side. In tennis, if you put top spin on one of the balls you hit, it can go up over the net and then dip down right behind it. In soccer, on a free kick, or any kick really, but you can curve the ball by putting a lot of spin and hitting it sideways. In golf, you can accidentally slice the ball by hitting it too hard and letting the club shaft bend back. Now it'll cause the ball to take a pattern more like this. So the similarity here is that each one of these sports involves a sphere that moves through the air with a direction. It does not just go straight and then drop down eventually. So this idea is applied to airsoft as well. And the idea in general is known as the Magnus effect. And the Magnus effect it's more about a theory of how spheres or cylinders react in an air tunnel, but it works if the sphere or cylinder is moving at a certain velocity in the environment because that will simulate the air moving towards it. It doesn't really matter what's moving, it's just how it reacts. So the idea here is that when you have, let's take these two BBs. This BB has no spin, this BB has backspin. So the Magnus effect and its idea is that there is a boundary layer of air around any spherical shape. Like essentially think of this as right like touching the surface of the BB. There is this boundary layer of air. And that layer of air, due to friction, moves with the BB. So if there's no spin at all, the boundary layer is only subject to the velocity that the BB is moving. So let's say both these BBs are moving forward. Right? That means that the boundary layer on the no spin is going to hit it. It's going to go around the BB. And then it's just going to kind of keep going. And there's not going to be much distortion there. I'm not a good artist, but you get what I mean. There's very little distortion. It's going to follow that path of the boundary of the BB. And then as it gets beyond the BB, it's going to keep following that straight line. Not much else happens. When you apply backspin, though, it changes the relationship. So let's say we have air coming in here, and then the thing that happens is that when you apply backspin to the BB, the side of the BB that goes the same direction as the air, right? So the BB is traveling this way. That means that the air is traveling this way. They're going to meet towards each other. So the air is going around the BB. It's actually kind of traveling like this, right? Well, if the BB is spinning this way, so on the top, it would be with the air. On the bottom, it would be against the air. Try to make it easier to see. So what happens when the BB is traveling with the air in this direction, it speeds up the velocity of the air. And conversely, it slows down the velocity of the air if it's traveling against. Now, just think of this in terms of friction, right? If something's moving against and they're rubbing up against each other, it'll slow it down. If it's moving with, it'll like bring it along and kind of help it forward, right? So this will apply Bernoulli's principle, which states that pressure and density are inversely proportional with objects. But this can also be applied to velocity. So what happens is that when the velocity is faster, the liquid, the air, or the fluid rather, is spread out more and therefore becomes less dense. It's the same amount of air. Remember, we're only working with that boundary layer, right? That's all we have. So because it's now faster on the top, which means it's less dense, it does two things. One, it travels more distance in the same amount of time as the air on the bottom. Now, this actually has nothing to do with Bernoulli's principle. This is just stating that if you have something on the top and something on the bottom, and this one's going faster, this one's going slower, it's going to eventually go like this, right? The one on the going faster will travel more distance in the same amount of time. That's just common sense. However, Bernoulli's principle says that this also creates a pressure difference, and this is the important part. So what this means is that the top part of the BB is going to be low pressure, and down here is going to be high pressure. So this means two things. One, again, the lower pressure on top, high pressure on bottom, objects want to move to lower pressure. So there's a lift force going on here. And the reason why it's lift is the first thing because the lower pressure, high pressure, where it's located. But secondly, notice how these two meet down here. Notice how it's not directly in the center here. It's lower. The fact that it's lower means that if you were to continue these lines, it would go something like this. And see how it started up here and it ends down here? This difference is going to make a whirlpool kind of effect here with a lot of turbulence and the air meets. This also contributes to the lift force. So it's the same idea with the moving air contributes to the lift. It's just whether you look at it with the turbulence location or you look at it with Bernoulli's principle with the low pressure, high pressure system. So what this means is that there is a lift force going on. And this is the Magnus effect is just combining all these principles and applying it to a sphere in the air to show that when you apply backspin, in the case of airsoft, it's backspin, there will be a lift force applied. Now, let's go back to the sports, right? If you are to throw a curveball, you apply side spin, not backspin. So it'd be around this kind of surface here, and then it would move side to side. It wouldn't move up and down. The sphere will move in the direction of the applied spin. So if you can see, the spin right here goes upward, and the force resulting of the spin is also upward. And this is kind of the application in airsoft. This is why we use this for airsoft, and why this Magnus effect kind of applies, is because this lift force counteracts the natural force of gravity, which goes this way. So think about it like if you have gravity acting on the BB, it's forcing it downward and accelerating the BB downward toward the ground. And now, due to Bernoulli's principle and the Magnus effect, this lift force is introduced that it won't cancel out gravity completely, but it will cancel out part of it, lowering the acceleration toward the ground and keeping the BB in the air longer. Now, that was a long explanation as to why this happens, but this is why the airsoft BBs happen. So now if we go back to the no-spin BB, because there's no applied lift force, the only force is the force of gravity, and that's it. So the BB will drop much faster than this one. So now I want to take that knowledge and talk about different hop-up levels, or just applying different amounts of hop-up, right? So if we have a situation where, let's say these are our BBs on the right, and then if we have no hop, a little bit, medium, and high, right? So we kind of already talked, no hop, you're not applying any lift force at all. It's going to go forward and then drop. If you apply a little bit of hop, it will stay in the air longer, but it's still going to drop eventually. It's not going to make a noticeable difference. If you apply like a medium amount of hop, or in this case, medium, I just mean like the accurate amount for your setup, which depends on the BB weight and the velocity and air volume and things like that. So the medium, or like the right amount of hop, it's going to go more like this, where you're going to see a little bit of a rise in the center. Not much, but a little bit. And this is where the tuning comes in place about how to find the exact perfect amount of hop is you want to get this little bump where it actually goes up a little bit, as low as possible, or tune it for a certain distance. So if you know that at 75 meters, your gun has a little bump, you can play around that and you can plan for that. Or you can tune it down and kind of get an in-between in this area here where it's you don't want the bump at all, but you want to have like maximum range without having any of the rise. And then too much hop up is going to go like this, where it goes way up and then it just drops right back down. So this one is when you can also see this if you ever use like 0.12 gram BBs in your airsoft gun, because the same amount of hop that works for a 0.3 gram is not the same for different weight BB. So if you put a really light BB in, almost any amount of hop will make it over hop, and you'll get an effect like this, where it goes straight up into the sky and then eventually just plops straight down. So kind of talking about that, what I just mentioned there is that BB weight matters. So if you have a heavier weight BB, it requires more hop up to counteract this effect, the just dropping effect. As the BBs get lighter, it will require less hop to counteract this no hop effect, or just the simple drop. Now, I'm assuming you guys all know that the way you apply hop up depends on the hop up and the arm itself, right? So what happens is that you will have a hop up, much like this one. Well, you know what? Let me use this one. You'll have a hop up like this one, and this hop up has the wheel and a lever arm in it. So in this specific setup, you can turn the wheel, and it will bend. So turn the wheel, and the arm will go like this to like this. It will start to go down, and there's a nub on the arm right here, which protrudes down into the barrel, and that will apply a force on the BB. It will touch the BB as it travels through, and this the friction force it will apply on the top as the BB goes forward will cause the backspin on the BB. I'm assuming most of you know that. That's just what a hop-up system is. That's how it works. But now, as this graphic I tried to show, is that as you move that lever arm down, as you turn the hop up on your hop-up, the angle that the nub contacts the BB changes. So, as this arm comes down, this would be like a correct angle, where you can see the contact surface between the BB and the nub is tangential, and this would be an incorrect angle, where it's clearly not, and the angle of the BB will go into the nub. The reason why you don't want this is simply that it's harder to tune. When you have a majority of the hop being applied by this little piece in the front and almost nothing by this piece in the back, it's going to lower the contact area, as first of all, which we'll talk about later, and it will also just make it harder to tune, because if you try to back this up now, let's say you want to move this up a little bit, it's going to more drastically affect the amount of hop, whereas if you just it had this perfect angle, and you moved it up a little bit, you're going to be able to more fine tune the amount of hop applied. And the reason being is because with this setup, the surface area is not proportional to the height of the arm. It also depends on the angle. So as you move it, because it doesn't move straight up, it moves at an angle like this, you'll be taking away more than you want to, and it will be harder to find the perfect height. Now, going off that idea is that there are different ways to kind of construct a hop arm. And this is going to be known, I'll call this one a standard. And this one is commonly known as a TDC mod, or top dead center mod. And the way these work is that for this standard hop arm, think of it like a seesaw. It's going to have one end that's usually either connected to a hop-up wheel or a rotary style hop-up, or something kind of like the example that we had here, where as you turn the wheel, there's going to be a track in the wheel that will move this point either up or down. And since the end moves up or down, think of it like a seesaw, this end will move the opposite direction. So if this point moves up, this point moves down. If this point moves down, this point moves up. Now, a top dead center mod isn't like that. The most common way to do this mod is to actually insert a screw right above the hop-up chamber in your airsoft gun. And when the screw contacts the arm, or some people even take out the arm completely and they just use a nub, you literally just take a screwdriver and you screw either in or out. So clockwise or counterclockwise. And what this does is that it moves the nub straight down or straight up, completely eliminating any. So now that you have eliminated the angle with the top dead center mod, you eliminate or not eliminate, but it increases the consistency in the ability for you to tune the amount of hop applied to the BB. And obviously that's important because, like we went back to the previous page I had, you don't want to apply too much, but you don't want to apply too little. You have to find that sweet spot that is different for every single setup, and that will be dependent on the BB type, the BB weight, your velocity, your air volume, stuff like that. It's all dependent on your gun setup. Now that we've talked about that, there are also different types of hop-ups. So the common types of hop-ups, I have some examples here, are going to be the rotary hop, which is the one that I had here with the wheel in the back. A wheel hop-up, or just a standard hop-up, or an old hop-up, it goes by a couple names, is going to be one like this that you've seen mostly in M4s. I've mutilated this area of it, actually. I was testing this years ago in a RetroArms split beta shell, and I was trying to modify this part to fit inside the split. So normally it looks like this. I'll put this hop-up here. This is the standard normal hop-up. It's just this one doesn't have the wheels on it. So this is going to be the one we use. And then the last one you have is a lever arm. Now the lever hop-up looks very different. It's common in AKs, and I think Masadas use it as well. But the lever hop-up will not have any wheels on it at all. It will have a piece on the top, similar to this, that would just go forward or back. And as this goes forward, it'll force the arm down like that. And as it goes back, it lets the arm sit up. So it's very similar to the angle of application we had in the last piece of paper. It just applies the angle differently, and that's kind of true for all of these. So all of these hop-ups, none of them are a TDC. None of them apply hop straight down, which means they all are subject to that angle problem, where, again, they will all work fine, but sometimes it'll be hard to find the perfect amount of hop in your setup because let's say you are at the perfect angle when you are applying this. Let's say you reach the perfect angle on a rotary hop-up. Right here, you have your BB, you have your nub, perfect angle. However, it's still not enough hop. The BBs are still falling too quickly, and they're not going as far as you know the setup should. You're going to have to increase the hop a little more. And once you increase it a little more, you are now slightly off angle, which means that it might be fine, but it means that as you increase the hop, now that you're off angle, your increments in how much hop is applied are going to be greater. And whenever you're doing something like an adjustment in bigger or larger increments, it means that the adjustment will be less precise, and there's a chance that the let's say the sweet spot, if you were to change this to like levels, like either spot 1, spot 2, spot 3, spot 4, not a dynamic, whatever you want. Think about it that way once you have an angle. Let's say your ideal spot would be in between spots 2 and 3, but you can't reach that. You either have a choice of spot 2 or spot 3 because the angle made the increment of hop adjustment too great. Now, you'll be fine with choosing 2 or 3, but it just won't be perfect. And when you're teching on a gun, you're building, let's say you're building a gun for long range, you're going to be anal about it. You're going to want to have that perfect spot in between the two adjustments. The wheel hop-up tends to have this angle problem less so than rotary hop-ups. But again, it still has the problem. It doesn't kind of escape the problem. And this is a generalization. I know, for example, ICS rotary hop-ups are actually very similar to a TDC, where they do apply hop almost exactly straight down. So in that situation, they're exempt from this angle failure, or angle problem, I should say. So it's really dependent on the exact type of hop and how they choose to apply. But this is true for, I'd say, 90% of the hop-ups within their respective categories. And the lever hop is actually the worst offender. This works the exact same way as a rotary hop-up. However, they are, for example, the ICS rotary hop-ups that are engineered to get around this problem. You don't have that option in a lever hop-up just because of how it's implemented in the guns it is. Now, again, this problem isn't huge, but it exists, and it's good to know about it if you are trying to fine-tune a DMR, for example. And the whole point of the build is to get the max precision, the max accuracy, the max consistency at long ranges. So now we're going to talk about nub types. So this is where most hop-up modifications are going to occur. It's going to be around changing the nubs and the contact type of your setup. So the most common nub type is just a normal nub. So this is going to be a view as if you're looking down the barrel, right? So you taking your gun apart, you have your hop up and your barrel set up all connected. So imagine that this is your hop up and you have a barrel coming off this. You've turned it like this and you're staring straight down. So these views are what you're seeing when you're staring straight down the barrel, if that makes sense. So this is going to be your standard nub. And the thing that happens here is that the BB sits right under it. This is going to be a flat nub. Some companies sell these now, but it started out as a modification a long time ago where you would either take a soft, rubbery sponge type material, or sometimes the people even took sorbo pads and cut those up. And you would just create a rectangle essentially and replace the normal round nub and mound on the bucking. And this is going to be a concave nub. So this one came across later. BB size is not going to be accurate, but essentially this one, it will be concave and try to match the shape of the sphere of the BB. And you can probably see these dots that I have. There's different types of nubs as well. There's hard nubs and soft nubs. Soft nubs are by and far way more popular than hard nubs for a few reasons. One, you want the surface, whether this is the nub or in this case it's also the this shape is also the mound on a bucking. So if you, for example, install either of these two nubs, the flat nub or the concave nub, you're supposed to also do a modification to your bucking that shaves off this mound, because that's the whole point, is you want to change the contact type, the contact surface on the BB. And if you keep that standard mound, that works fine with the standard nub that literally sits right in there, the whole point is to get rid of that. So these are kind of like the three main types. So going back over here, different types of nubs. It's hard and soft. And this is strictly just like the material it's made out of. It has nothing to do with the shape, where these are mostly the shape. This is mostly the material. And hard nubs are popular for these concave style ones because you don't want this to deform. You don't want this to change its shape. It's already pre-made to kind of hug the wall of the BB or the outside of the BB. And that's exactly how you want it. So you want this to be hard. Now, the other ones, you don't want that. So if you notice, see how this, the concave nub, it has a lot more contact surface with the BB than these ones do. The reason why, well, not the reason why, like it just does. This has way more contact surface because it literally wraps around and hugs the BB. This is why these two types are commonly soft. When the BB hits them, so let's redraw this. So this isn't actually how it looks when the BB hits them. It's going to look more like this. Or like this. Because since these nubs are soft, they deform to the BB. So it will actually be like this, which mimics the concave shape. However, the difference here is that these started as a soft material and it naturally forms around the BB. However, the BB happens to come across and hit it. So this is just examples of different types and why some are hard, some are soft. Now I'm gonna build off this on the next page with some lateral consistency and differences between the nubs themselves. So again, this is view is looking down the barrel from the hop up, just like I showed last time. And the lateral consistency, it concerns the nozzle bucking nub and chamber and how they all fit up and how they all align and how this is a bit different for every setup, but it also, or the main part is actually here. It's the nub and how the BB lines up with the nub in your setup. So now, if we come over here, you'll notice that I have the 3 common types of nubs again, kind of back from the last page. So the thing is, let's say you have a dead center application, right? So the BB hits dead center in the respective nub. In this one, perfectly fine. There's no issues at all. This is how airsoft guns were designed. That's how they were originally intended to work. The concave, again, this is what it was made. It was made to hug the BB and hold that shape. And then the soft flat nub, same idea as the one up here. It forms around the BB and it will end up working fine. All of these work as intended, but they should. This is the BB straight down the center, lined up properly, no issues. That's not how it actually happens. A lot of the times in airsoft guns, now this is exaggerated so you can see the difference, but the BB might enter the hop up slightly misaligned. So in this case, this is center of the BB, right? So this BB is misaligned. And what happens is that this puts spin on it in that direction. And if you remember from the very first page when I'm explaining the Magnus effect, that means that the pressure difference is going to be right around here, and it's going to force in the same direction as the spin. Remember how the force generated is always the same direction as the spin, which means this BB is going to go like this when it leaves that barrel. And here is going to have the same effect, but the opposite direction. It's going to put spin on it in that direction, which is going to cause it to go like this. Now, we don't want that. So this is where you'll get BBs that hook or that curve, and they're not going straight. When this happens, it means either your nub or your bucking is misaligned. It might be at an angle, it might be to the side, something might be wrong. Or, remember over here, your nozzle bucking nub and chamber combination is loading the BBs inconsistently, and it is not loading the BBs and securing them the same place every time. So now let's look at the next hop design. The concave nub or surface also has a way of kind of fixing this problem. So even though it's not perfectly centered, it's still pretty much trapped in this, because remember, these are usually harder, tougher surfaces that don't deform as easily. I'll talk about Rhop patches on the next page, but remember, if you're not using a patch, you usually use a hard nub for these types of the concave nubs or the H nubs. H nubs are another one where they essentially just come down on the side like this. It's just instead of being concave to the BB, it's kind of like a point here and a point here. It acts as the exact same purpose of having more contact and different points than just a little bead on the top. And the reason why both of these work in the consistency department is that there's less room for error of the BB. If the BB is a little off to the right, it still has to fit into this shape. So even if it's a little off, it's still going to be contacted about by the same surface area. It might be a little different. So again, I exaggerated greatly, but see how on this side it's not touching? It might be a little off, but it's not going to be anywhere near as off as the normal mount and nub combo. And same with this, just the opposite side. So this might be a little bit off, not much. And now the bottom part, this is the flat nubs, the rectangle nubs. This is the most common modification for a hop-up, is that you shave the mound off the bucking and then install a flat nub, and it changes the surface contact to this flat shape that will form around the BB and kind of make this concave shape wherever the BB happens to lie. And the reason why this is so popular is because even if the BB's dead center or off to the side, either way, it has a very large margin of error. The BB can afford to be this far off, and it still has a straight application of hop, because the mound, or the lack of mound rather, the square nub, still applies an even application of hop up on the BB. It does not change the shape of the spin like it would for the mound and nub up here. And same here, right? The actual hop is still the exact same, even though the BB was inconsistently loaded by the gun. And that's why this hop is the most common for modification wise, is because without extensive modification, which in that case this one would probably be the best, this one increases consistency and it lowers the margin of error caused by other parts in the system. So it's an easy modification to do that will increase the consistency in the overall range of your gun no matter what. It will always increase it, unless you're going from a highly tuned setup already going down to this, where it won't hurt it that much, but it just might not make it any better. The last thing I want to talk about are R-hops and similar patches. And I'm sure you've heard the term R-hop or S-hop or G-hop thrown around the community for a while. And the idea is that you're including this patch that will just kind of sit on the barrel. I can try and draw here a little bit. So the red is going to be the barrel of the airsoft gun, and the black is the patch that you're installing over the hop window. That normally this is where the arm would push the nub into the bucking, and the nub and the mound would go down and cause all that stuff I showed you on the last page. Now instead you're putting this little patch to cover the window. So instead of the bucking material being what touches the BB, it's the material and shape of this patch, and the shape part is the more important part. You might remember this. This is that concave shape I showed you on the last page. So now this is back to that barrel view of you're looking straight down like this on the page. So this would be the surface of the R-hop patch. And now you're going to have a bucking on top of here that's like this, and the BB on the inside. And the reason why this one is really popular is because sorry, I think I said bucking. I meant nub on top of here, the nub. The reason why this is very popular is because it combines the two things from the previous page, where the soft, flat, rectangular nub that lowers your margin of error and increases consistency, plus the concave contact shape of the patch. And the reason why, this is not hard plastic. This is going to be, it's still going to be a stiff rubber, but it's still rubber. It's moldable. It's not, so it's going to hold its shape somewhat, but it's not going to be so stiff that the BB will not be able to let this conform to its edges a little bit if it is a little off center. And the biggest advantage of this is that it applies hop at the most surface area possible. So it mimics that concave nub, but instead of the nub having to push a bucking down onto the BB, this patch just sits right on top of it. And the other benefit of it is, see how long the patch is compared to before, where the window is this whole thing. The patch covers the entire window. So if you have a nub, a rectangular nub, then let me grab another color, that sits on it like this, it's going to push the patch down along the whole length of the window. Whereas previously, you just had a nub that was about this sized. Hopefully that shows up. and only that part of the bucking was being pushed down. So even though this view looks very similar to the concave nub, it extends a lot longer. Imagine this is 3D and it goes into the page. This is way longer than just the concave nub. And that kind of gets to the next topic, light versus heavy BBs. I mentioned earlier that lighter BBs require less hop, which means that this R-hop patch, the extended patch that applies over the length of the BB and it enables you to apply more spin, is better for heavier BBs. You're usually not going to see much of a benefit of R-hop over just a normal flat hop mod until you get upwards of 0.3 gram, and some people even don't see a benefit at all until 0.36 gram or higher. Again, that's dependent on the specific gun, your setup, your velocity, and all that kind of stuff. But that's a general rule of thumb, is that these types of mods are for heavier BBs, because what they allow you to do is apply more hop. Now, the last thing they allow you to do is up the consistency in terms of how the hop is applied, or how the spin is applied to the BB. So we're going to go on that same idea we had before. So going back to the same idea before of the longer patch allows you to apply hop over a longer area on the BB. It allows you to apply less hop and touch the BB less. So a good way to think about it is that, now think of this as a top down. Remember, this is the same view, like this is the window here. So this is your nub. If you have to apply, if you were to call hop, if you were to make it like levels in a video game, you have to apply seven amount of hop on your specific application. That's just what yours requires. In order to do that with this tiny little surface area, it needs to go pretty far down. It needs to really smack that BB to apply enough spin, which also slows the BB down significantly. With this patch, because you can apply the hop over this whole area, as opposed to just this one, you can touch it or like impact the BB less. You can apply a smaller force that will not sit there and block the BB's path. It will just kind of skim the top of it. Because that force is applied over a longer period of time, you can achieve the same amount of spin as this tiny one that was pushed way far down into the barrel. Now, extending that, you have ER hops, or extended R hops, and these don't have much of an application unless you're pushing really, really heavyweight BBs, maybe some ceramic BBs like the 0.66, 0.69 grams. Or you have a very high velocity, very high joule output gun. Like I have one airsoft gun that uses this ER hop window, and I honestly don't think it's worth it because I don't use these ceramic BBs at all. I have 0.45 grams, and that's the heaviest that I ever go. And I would say that this provides such a minimal increase in performance over a standard R-hop patch in my personal experience for those applications that I don't think they're very worth it. But if we had this in like a theoretical situation where we could go up to like a 1.5 gram BB and insane joule outputs, then this would be absolutely worth it, because you would want that extra level of tuning and the lower variability for those heavier weight BBs. Because again, same idea. For the heavier weights, this amount of distance might not be enough, and you might have to start pushing this further and further down into the barrel, further obstructing the BB to get the required hop, where this one does not need to be pushed down nearly as far. And that's about it, guys. That is the general overview of why the hop-up works in the first place, why your BBs stay in the air, and why hop-up is even a thing. Different types of hop-ups, patches, nubs, different applications, the differences between them, and why some mods are used. Again, like I said in the beginning, this is going to be a longer video, a lot of talking and explaining, and it's really just more to get the knowledge floor raised, not to teach very experienced people in the hobby new topics. I'm sure anyone who watched this video learned one or two things, but like I said, it is geared more towards entry-level airsofters. So I will have, hopefully, more of a series turned out of this, where I'll make videos on other topics as well. But this was the most requested by far, so I wanted to do a video on it. Hope this helped you guys. If it did, let me know. If there's anything you want me to change and improve, please let me know. Obviously, this is not the most professional quality video or setup. Um, I'm just kind of working with what I have to get my knowledge and information out to you guys. So hopefully I will see you again, and I hope this helped. See ya.